we have a dihydrogen molecule. We need to break this hydrogen-hydrogen bond. Okay, so like this. If we want to break this hydrogen-hydrogen bond, we can either perform a homolytic cleavage or heterolytic cleavage. In homolytic cleavage, we break hydrogen to its elemental form. This reaction, as you can see, is highly endothermic. It requires high temperature. This bond is relatively one of the very strong bond in the nature of 436 kilojoule per mole. Okay. So either we can use high temperature to break the bond, or in an alternative way we can make use of a catalyst to bring down the activation energy for this reaction. One of the way to do homolytic cleavage is the use of noble metal like platinum, which can get easily oxidized relatively in the presence of hydrogen. Okay, if we have a platinum surface and a high pressure of hydrogen on this surface at a significantly elevated temperature, we can break the hydrogen bond and the platinum will be oxidized. This can be regarded as oxidative addition at the platinum center. Okay, by the adsorption at the metal surface. Okay, we can just make a note here. Okay, sorry, some problem. Okay, adsorption at the metal surface. So by this way we can break the hydrogen bond. Okay. So this form of hydrogen is very reactive. This is what we do in the many organic reaction where we need to hydrogenate the unsaturated bonds. Either we take palladium or platinum. Palladium along with some carbon, which is called palladium graphite, used as reducing agent. Okay. Efforts has been made to understand how this homolytic cleavage is happening. It is very difficult to do characterization at the surface because it does not give direct evidences. Most of them are indirect evidences through infrared spectroscopy and other spectroscopic techniques. Okay, so chemists started perusing activation of dihydrogen at the single metal or single coordination sphere of the metal. Okay. Here Ml is a coordination complex or organometallic compound. Okay. Either a organometallic compound. So if we bring in the dihydrogen molecule which has a bond length of 0.8 to 1 angstrom. Okay, if the metal is in low oxidation state, it can donate electrons to the antibonding orbitals of the dihydrogen molecule. Thereby the bond order got decreasing and the hydrogen-hydrogen bond starts elongating. As you give more and more electron density to the hydrogen molecule, it starts elongating. Okay. So further increase of electron density from the metal to dihydrogen elongates and it almost goes to a dihydrate state. Okay, so this is actually a dihydrate state. Okay, so these various forms of dihydrogen, the normal, elongated and the dihydrate, have been experimentally observed in many of the isolated complexes. This actually find application in numerous reactions. For example, the famous rhodium catalyst, that is Wilkinson catalyst. Okay, it has profound applications. Okay, the other way to cleave the hydrogen-hydrogen bond is by heterolytic method. In this method, we have hydrogen cleaved to H plus and H minus. This normally occurs through adsorption at the metal oxide surface, where metal, here zinc is electropositive and the oxygen being electronegative. So the hydride, that is H minus, got added to the zinc center and proton gets added to the electronegative oxygen center. Okay, by this method we can heterolytically cleave the hydrogen molecule to form protons and hydrides attached to the respective atoms. Okay, so this form of reaction is actually happening when the carbon monoxide hydrogenated to methanol in presence of copper, zinc oxide, and along with alumina. Okay, so in all the previous cases we used transition metals like zinc or platinum or palladium for the hydrogenation. Very recently there had efforts to check whether p-block elements can do the same. Okay, here in this reaction we have an acid, okay, borane. It is an electron deficient boron species, and here it is, and we have a electron rich phosphine species which have a lone pair of electron, Lewis base. Okay, this is Lewis base and this is Lewis acid. Normally a Lewis acid base pair like ammonia and BF3, they interact to form a dative bond. Here we try to increase the steric around both Lewis acidic and basic centers, so they can't interact very much like the ammonia and BF3. So the phosphines have aryl group around it, very bulky, and also boron have also steric hindrances. So this prevents the boron interacting with the phosphorus center. So we can't have an acid base pair, but there can be weak interactions between the groups in phosphorus and boron like this. Okay, I'm just trying to mark them. Just a weak interaction is being found between the respective groups. Okay. Okay. In this condition, when we introduce the hydrogen, they heterolytically cleave into H- and which is base, and which goes to Lewis acidic boron center, and the H plus will go to Lewis basic phosphine. Okay, so in this way we can cleave hydrogen heterolytically. Okay, once we have cleaved, we can have it use it for the reduction reactions. Okay. Thank you.